Hi, everybody. So my name is Stefan Lalonde, and I'm really excited to be here to talk to you about fossils and biosignatures on the primitive Earth. Just before we start, a little bit about me. I'm Canadian. I did my Bachelor of Science at McGill University, Master's and PhD at the University of Alberta. I defended my habilitation in 2018, titled Biogeochemistry of the Early Earth, Insight from Archean and Proterozoic Sedimentary Records. So gives you a good idea of what my expertise is, which is early Earth sedimentary records, early traces of life, the evolution of biogeochemical cycling, and generally geochemical and isotopic reconstruction of Earth's surface environments. And I have a couple example projects here that I've been involved in over the years, whether they be to develop new isotope tools or, and some of them are drilling projects to access exciting new samples of the early Earth. So a quick outline of what we're going to talk about today. I want to talk about early Earth fossils and biosignatures. What exactly are we talking about when we talk about these fossils and biosignatures? Then I want to talk about where do we find them? Hint, hint, ancient rocks. Then I kind of wanted to do something fun for you today. So I decided to make a countdown of Earth's top 10 greatest hits of early life, plus some honorable mentions. And then, and what about Mars? As you may see in this cartoon here, I totally don't agree. Even if I may be a world expert on prehistoric algae, I think it's pretty amazing stuff. So what exactly are we talking about when we talk about fossils and biosignatures of the early Earth? Well, let's just wrap our head around timescales of the early Earth. Here you have the geological timescale from the Geological Society of America, not actually to scale. The part in red here, it represents 7/8 of Earth's history, but it's compressed here into one little quarter. And if we want to really think about the real scale here, if you stretch your arm out sideways and the origin of the Earth is your shoulder, multicellular life and plant life starts around your fingers. Okay, and so we're going to be talking about this whole part of the arm and even the part before the elbow. Today we're going to spend almost all of our time talking about life before 2 billion years ago, so before the elbow. Okay, to give you a perspective on all this. And the history of humanity is removed with from your fingertip with one swipe of a nail file. Okay. So here's a better, more accurate representation of geological time with an expansion on the Phanerozoic and multiple evolutionary events of note. Okay, so when we're talking about geological time, here's a kind of a simplified version where you can see plants, animals, eukaryotes, and bacteria and archaea. We're talking about, before 2 billion years ago, we're talking largely about prokaryotes, bacteria and archaea. Okay? And the context for this is also nicely summarized in this slide, where you can see oxygen concentrations in red, which are vanishingly low until the Great Oxidation Event 2.5 billion years ago. And you can also see iron concentrations in seawater that are quite high because iron is soluble under these conditions, and it eventually gets titrated out as oxygen accumulates in Earth's surface. So it kind of sets the context of the time we're talking about, what kind of conditions these fossils lived in. Okay, so when we're talking about these fossils, one of our first, if we're talking about prokaryotic fossils, one of the first things you might think about are, well, fossilized cells, microfossils. And what you have here are a variety of sponge cells. And sponges are quite interesting as a primitive animal. They're kind of at the limit of multicellularity. Some sponges, you can actually disaggregate them into individual cells, pass them through a sieve, and they'll make a sponge again. So we're kind of really here at something that's quite at the limit between multicellular and unicellular. And you can see that the cells can be quite characteristic and distinct. If you found one of these in a rock, you might be able to say, well, I can identify this organism. Well, that seems kind of simple for complex cells like sponges, but bacteria don't have complex forms necessarily, and there's an even more important problem when we're talking about bacterial fossils. Here, what are these? None of them are cells. These are what we call biomorphs. They're made in a laboratory, precipitated using, say, barite or silica, and they resemble bacterial cells. So I'm almost not going to talk about microfossil evidence in my top 10 hits. this issue of the non-specificity and the lack of confidence in microfossils and fossilized cells is pretty evident in a very large debate that happened in the 1990s and early 2000s. And we're talking about the Schopf versus Brazier debate. So in 1993, Bill Schopf published this article in Science showing claiming microfossils that resembled cyanobacteria in the 3.46 billion-year-old apex chert in Australia. And so this was directly countered by Martin Brazier in 2002, looking at the exact same samples that he got from Schopf, realized that these lovely structures that look like cyanobacteria or filamentous organisms in any case, in fact, have features that don't resemble cells at all. They're branching. Cyanobacterial cells don't do that, or bacterial cells don't tend to do this. Some of them have actually kind of quite complex structures when you image deeper into the thin sections. So what happened was that Brazier did some Z stacking and imaged different focal planes and combined them together to show us a better idea of the real structure of these things. And they don't really resemble cells at all. Actually, even worse, they don't even come from an environment, from a surface environment. It turns out that better follow-up field geology revealed that these microfossils that were the subject of Schopf's paper come from a feeder dike or feeder vein of silica that was pretty far disconnected from the surface silica deposits. So cyanobacteria living 100 meters deep in a hydrothermal vent fissure seems quite unlikely. So we're not going to talk too much about microfossils because bacteria just don't leave really great individual fossils, generally speaking. So we might be talking about stromatolites. This is something that maybe you will all have heard of in this room. Just quite briefly, what is a stromatolite? I'm not going to go into much detail at all, so I've deliberately chosen a very simple cartoon that basically shows this organo-mineral structure with a complex microbial community living on the surface and inside, and the metabolic activities of which are fueling growth of the structure. Okay, and we can have them, typically we find them in carbonate, but we can find them in other minerals as well. But it's quite complicated. This diagram shows just the non-photosynthetic reactions, the organic carbon consuming reactions that would occur in a structure like this, and all of the various cations and sources and losses of bicarbonate. So it's quite complicated. We're not going to get into any more detail on that, other than they're quite nice structures because they can be quite specific to life. And we shouldn't actually be talking about stromatolites. We should be talking about something called microbialites, of which stromatolites is a subcategory. So here you can see microbialites include all sediments that were formed under clear microbial influence. Okay, and so they can be classified based on their macrostructure, on their mesostructure, and stromatolite is one that is laminated and layered. However, you also have thrombolites that may take these different macrostructures, but lack this clear internal lamination and layering and be clotted, hence the word thrombo. Okay, so, and then we also have to be careful is that there are some structures that can resemble microbialites generally that are non-microbial in origin. There's one last kind of microbialite that I want to highlight especially. This MIS stands for microbially induced sedimentary structure. And here we're talking more about, say, microbial mats that have rolled up or ripped up and been preserved as such in the rock. And they're not making a calcareous structure that's growing to the sun, per se, but they still leave microbial structures in the sediment. And we'll look at that a little bit later. And shameless plug for a recent paper of ours, we've recently established the first museum microbialite collection at the Natural History Museum of Paris. So feel free to contact geological curator Pierre Saint-Joffre if you want access to this microbialite collection that includes now over 1,400 specimens from around the world and all different times. So and you can find data describing that collection in this article. When we're talking about these microbialites, and I might use microbialite and stromatolite a bit loosely interchangeably, they show a great diversity of forms that, based on studies, for example, in their rare modern occurrences, like in Sharks Bay, Western Australia, we can relate this diversity of structure to different depositional environments and hydrologic regimes and water depths and et cetera, et cetera. So here's a nice little example of how you get this kind of diversity of microbialite structures like I showed you in the previous slide. And you can also look at their diversity through geological time. When people first started studying stromatolites, they would name them like plants. They would assign them taxons, and you could count the diversity of stromatolite taxa through time. It's very much a plant systematic type approach. And what you see here is kind of increasing diversity in microbialites and stromatolites through geological time, with a really important decline right about here that most people attribute to the fact that the multicellular biosphere exploded, and microbial mats and the bacteria that formed the basis of these stromatolites were now suddenly at the bottom of the food chain. And so microbialites, as a consequence, microbialites and stromatolites don't typically form in most environments today because other things eat them before they can grow a structure. And what we see today are, where we find stromatolites today are in extreme environments, hypersaline lagoons, hydrothermal ponds, where the conditions are too extreme for their predators, which is often eukaryotic life, going from single-cell eukaryotes all the way to animals. And we're going to be focusing a lot on, when we get to our top 10 best hits, we're going to be focused on only records before 2.5 billion years ago. So we're really going into the rarest, the jewels of our really ancient rock record today. That's kind of my goal. Just a quick word about some of these false stromatolites. Everything you see in this picture, and this is a really interesting study, all of this is paint from a car factory floor where they paint cars. And the paint is just accumulated over time and made structures that look like this. So we have to be careful when we're talking about stromatolites and biogenicity. And this is something that's debated. And in fact, most of the things that I'm going to show you, whether they be fossils or biosignatures, because of their rare and ancient nature, are debated. And this is an excellent example of why this kind of debate is important. Okay, now we might also think about biomarkers, or what some people call molecular fossils, organic remnants of living material that may degrade into degradation products that are still recognizable, attributable to some kind of source. And this has led to quite some controversy as well in literature. And in my top 10, there will be no biomarkers featured. And I'll explain here briefly why. This was a really exciting paper in 1999 by Brox and colleagues looking at Archean molecular fossils and the early rise of eukaryotes. And they analyzed drill core from Western Australia that was 2.4 5 to 2.6 billion years old. And what you have here on this column here are steranes that they're finding in this organic carbon-rich drill core from Western Australia. And here they're finding what are called 2-methylhopanes. These are cyanobacterial biomarkers, and these are eukaryotic biomarkers. However, follow-up study, and there's been two kind of let's say high impact papers that re-examine these exact same drill cores. And here what you can see are analysis of steranes and hopanes, so eukaryotic biomarkers and cyanobacterial biomarkers from the surfaces of the rock that were cut with saws, from the rounded surface of the drill core, and this is from very carefully prepared drill core interiors, where the biomarkers are no longer present. They're almost certainly a surface contamination of these drill cores sitting around in a core shed for 10 or 20 years or more. So, in fact, there is no confirmed biomarker that we have any kind of appreciable confidence in that's older than 1.73 billion years old. And this is the reference for the current limit of where we can take the biomarker record. And everything I'm going to talk about today is way older. So let's get going. Finally, before we get going, I want to talk about metabolic and redox signatures. And this is, we might seek to identify ancient life by its metabolic waste products or isotopic fingerprints of sulfur cycling or iron cycling and these kind of things. And so this gives you a pretty accurate state-of-the-art of when we think different metabolic pathways evolved on Earth and for which there are evidence. And it's all summarized by Kevin Lepeau in a 2020 Year Science Review. And what you can see here is that before 2.5 billion years ago, things get pretty shaky. You know, we don't really always know how the fossils and the biomarkers we look at are how those organisms were really living. And towards the end of my talk, I'm going to try to get to that question if we have time. So now wait a second. Didn't I just tell you there's a whole bunch of microbialites and stromatolites in these ancient rocks? You know, we know they go back quite far. Can't we say they were doing oxygenic photosynthesis? At least if we take this example, of oxygenic photosynthesis, okay, we can't really put it much further than 2.5 billion years ago with appreciable confidence. What happened 2.5 billion years ago? Well, the atmosphere was oxygenated, and that places a firm lower bound for the function of oxygenic photosynthesis. But how much far back does it go? And this is actually probably the biggest fruit on this metabolic tree, because it's the metabolism that defines Earth as a habitable planet. You know, something like they say over 98% of biomass either comes from oxygenic photosynthesis or eats it. So, you know, when we talk about this blue-green planet that we have, we're really talking about this metabolism, and everything else are kind of scavengers, you know, in today's world. So it's been a major target for ancient metabolic biosignatures. And so, you know, here are a bunch of stromatolites. They're all older than 2.7. They're all in the period when we don't really know if oxygenic photosynthesis was operating or not. The problem is we can't attribute these directly to oxygen-producing organisms because there are several kinds of photosynthesis on Earth. We have oxygenic photosynthesis, the kind that produces free O2 that we see all around us in the trees and the grass and that dominate the water columns of lakes and oceans today. And then we also have anoxygenic photosynthesis. And this is it seems to be a more ancestral form. And it depends on the oxidation of sulfide to elemental sulfur or sulfate, and ferrous iron to ferric iron using light. And it's here you can see it's quite rare today because these poor organisms, it's a miracle they still exist today because they need to be in anoxic waters with abundant H2S or iron 2 available and be in the photic zone. In today's oxygenated world, it's quite rare. So we find them in really heavily stratified systems where the redox mostly in lakes, where the redox stratification reaches up into the photic zone. But it's quite rare today. Okay, so I just want to give I've been trying to kind of give some words of caution on some of these biosignatures. You know, this is a paper where most of the data was generated in Brest when Professor Planavsky was visiting during his postdoc studies, and it was my postdoc supervisor who is the senior author on this. They looked at sediments in Suzy group, 2.96 billion years old in South Africa that are here in gray. And what we did is we analyzed the molybdenum stable isotope composition. And I'm not going to go into too much detail here, but I'll give you kind of the gist. Is that today, molybdenum isotopes in seawater are heavy. They're above 0. So this is isotopically heavy, and this is isotopically light when we have negative values. And the reason why seawater is heavy today is because manganese oxides, like vernadite, remove molybdenum with a 3 per mil fractionation, preferring the light isotope. So if you form a manganese oxide from isotopically heavy modern seawater, it's 3 per mil lighter. And this is kind of a way to try to, this tool permits us to try to look for manganese oxides when they may not be preserved. Manganese oxides actually don't really survive burial in sediments. They're a great thing to breathe on an anoxic world. And even today, it's rare that you get manganese oxide surviving diagenesis. It's reduced to manganese to reduce manganese. So this isotopic tool kind of lets us see through that diagenetic reduction. And you can see here, all of these points here, these are banded iron formations of different ages, and the black points are 2.96 billion-year-old banded iron formations that go isotopically very light in molybdenum as they get more and more rich in manganese, which is a telltale sign of manganese oxidation, even if these rocks contain no manganese. So that's this is the kind of thing that this is for a long time represented the best evidence for oxygenic photosynthesis before the GOE at 2.96 billion years ago. However, there's been some issues. In the last couple of years, we realized that a lot of these redox proxies that we use are highly sensitive to modern weathering. So this is excellent work by Ronnie Schoenberg's group. They went back to the same outcrops and they also sampled these the same iron formation that you saw in the previous figure in drill core, and they find an important contrast in the isotopic composition between drill core and outcrop, showing that in fact there is some mobility of these signatures at Earth's surface, which is a major problem for us that hopefully we might be able to talk about it at the end. Okay, moving on with things. So, quickly, where do we find these ancient records of early life on Earth? I'll go kind of quickly here. This is the age of the oceanic lithosphere. And you can see that nothing here is older than 280 million years old because it's rapidly produced at mid-ocean ridges and generally destroyed by subduction. And contrast this with the age of the continents. And this time we're in billions of years. Okay, so when we're looking for these multi-billion-year-old biosignatures, we're looking at the oldest, generally the oldest parts preserved of the Earth that are preserved on the continents. And here's a quick zoom onto North America that shows you where you can see the different ages of crust that were kind of slapped on or accreted to the growing continent over time. And you can see how North America grew outwards from Archean rocks at the center, and you can kind of follow its progression outwards. So often we're finding it's the old centers of continents where we find these records. Okay, and just a quick word about how these records survive. In fact, almost all of these rocks older than 2.5 billion years ago have been heavily metamorphosed. They've been buried, they've been cooked. Okay, and so here's a little bit of lingo that might help you. This is kind of a metamorphic pathway in temperature, pressure, space for rocks, leading up, and then basically retrograde metamorphism, kind of uncooking on the way back. And as you can see, you can see in this trajectory here, all the rocks I'm going to show you are green schist facies metamorphism, and the oldest ones have reached amphibolite facies metamorphism. And I think it's important to highlight that as we go forward. So you know that these rocks aren't just sitting there pristine. Some of them have seen some pretty traumatic histories in terms of burial and metamorphism. Okay, so let's do a top 10 greatest hits of early life. This is just my perspective. I think if you would have asked any researcher looking at early Earth records, they would have made a different set of top 10 hits. So I'm just giving you my 2025 selection to count down the year. All right, so starting at number 10, I want to talk about the Campbell-Wren-Malmani carbonate platform. Okay, so here we are in South Africa, and here it outcrops over 800 kilometers. There's a 100-kilometer scale bar. This is remarkable. This is Earth's first truly large carbonate platform. It's aged from 2.52 to 2.6 billion years old, and it shows remarkable stromatolite diversity. Here's a photo from the field from a locality called Butsap, and I have a piece here for you where you can see this rock that came from the Campbell-Wren-Malmani platform. And what you can see is it's got these beautiful columnar stromatolites. You can see this one is branching here, which is quite characteristic of life. You can also see how brown the fine carbonate mud fill in between the stromatolite columns, how brown it is. Well, that's because it's extremely iron rich, having been formed before the Great Oxidation Event. You don't find generally carbonates like this iron rich after the Great Oxidation Event. Now, the Campbell-Wren-Malmani platform, there's a lot of things that are really interesting about it. One of the things that's quite interesting is that it contains Earth's largest stromatolites. Okay, I know it's hard to get an idea of scale here. Where are the stromatolites? Well, that is one, and that is one, and that is one, and that is one. And in fact, you can follow it all up this quarry wall of this ancient kind of mine site. Let's look at another picture for perspective. Here you can see the stromatolites, okay, the big domes, and there are people for scale. Yeah, so I thought that Campbell-Wren-Malmani deserves the number 10 spot on my list. Okay, moving forward to number 9, I'd like to highlight the Tumbiana and Ventersdorp supergroups. It's a tie. Here you can see the two stromatolites from the 2.72 Tumbiana formation, which is in Western Australia, and here are stromatolites from the equivalent age Ventersdorp supergroup in South Africa, and both of these are lacustrine deposits. almost represent Earth's oldest lake. There is one known lacustrine deposit even older, but these are the most well studied, and they have these spectacular stromatolites, which I'm not aware that there are the stromatolites in the older lacustrine deposit. What is also quite remarkable in the case of the Ventersdorp group, we did some research in 2019 looking at fossilized bubbles in the stromatolites. You can actually have what we call a fenestrate microbialite. That means it has fenestrate, has windows. And what are these windows typically? They seem to have been cavities that are filled in later, gas cavities. And so what we saw in this case is that we see these kind of fossilized bubbles, these fenestrate fabrics, and we see iron oxides coating them preferentially. They're not full of air now. They have been completely filled and probably filled quite some time ago. What's quite remarkable is that in situ geochemical data obtained by laser ablation ICP-MS shows dramatic negative anomalies in cerium here, which cerium is the only rare earth element that's susceptible to being oxidized under surface conditions in the presence of O2. And so what we can actually see the signature of cerium oxidation occurring on the bubble on the bubble rim walls. So we suggested that here we actually these bubbles are probably oxygen bubbles. But you know, the other thing is that these rocks are also heavily altered. So I say that with a grain of salt, and it rests to be confirmed. Okay, and that's a kind of little schematic of what we what we proposed was occurring. Okay, going to number 8, the Mosher carbonate in the Steep Rock Lake group. So here where we are is we're right now in, I know the screen's not very clear, we're now in Canada. It's 2.78 billion years old in Western Ontario. And we have here a carbonate platform that's 400 meters thick. It's associated with iron formation and manganese formation. The preservation here is excellent. This is really one of the lowest grade stromatolite occurrences of the Archean in terms of metamorphic grade. And we also see fenestrae, just like we saw in the Ventersdorp bubble study. And we see evidence for O2 production. Here, unfortunately, the site is it's in where you can see the outcrops the best. You have these spectacular quarry walls just completely full of stromatolites. It's a former mine site, and it's a disaster site. It's leaking pH 2 water, and the whole thing is shut down, and no one is allowed to go in anymore. Even research scientists, it's completely shut down to everybody. So hopefully you got your samples early. I'd like to show you a sample here from there. So here are some images of some of the stromatolites from the Steep Rock Lake group. Here you can see some giant domes, and I'll touch another word on that. You can see some nice smaller domical stromatolites, some columnar stromatolites, and here we have the fenestrae, you know, where this late white calcite infilling is interpreted to have filled gas cavities. And so I have a piece of it here. That maybe you can see the fenestrae in it. And notice how black it is, all that organic carbon that's still there in this stromatolite. It's quite remarkable because it's so fresh. In Canada, we haven't had deep oxidative weathering like in South Africa or in Australia. It's really a great place to look for these kind of rocks because it was recently deglaciated. So we get away from a lot of the deep surface weathering that affects a lot of the older records. So, okay. So here's some evidence for that O2 production in the form of, again, negative cerium anomalies that are quite important. These are up until these are the largest ones reported in literature for the Archean. And here are some. It also features really large stromatolites, and that is me as a master's student in 2007, just loving my life and having a blast on this giant stromatolite. Okay, then we're going to number 7 at Red Lake and Woodman Lake, where we have 2 carbonate platforms aged 2.87 to 2.85 billion years old. And this is Earth's oldest, and I'm going to thick carbonate platforms. Older than this, we're not really finding any really thick carbonates on Earth. And I'll talk about why that's important in a second. There's abundant microbialites, and I have a piece here. This is from the 2.87 billion year old Red Lake carbonate platform, and these are the oldest fossils that are non-controversial on Earth from the northern hemisphere. Everything older is from the southern hemisphere. That's considered a non-controversial. So this is a pretty important site. It's relatively unknown. There had been one article describing one little outcrop with stromatolites until a gold company drilled it multiple campaigns in 2010, 12, 13, and they produced something like 6 kilometers of drill core, of which I have 1.5 kilometers at my institute now. And so it's quite nice. It cost them over $30 million to drill that drill core up in northern Canada, and they were going to throw it all out. For your information. This is a really recent paper, came out in 2025 from a project that we all had together looking to put new age constraints on carbonates that are occurring all across the superior craton of Archean carbonates. You can't really see it here, but they're all lined up within error age. And it hints at actually a very large carbonate platform around 2.87 to 2.85 billion years ago in northern Canada that has been largely unexplored. One paper since the 80s until we started looking at it a couple of years ago. And so here's some photos, beautiful microbialites here. The exposure is not as great. There's no big quarries to go see giant walls of stromatolites. So this is lakeshore geology. There's trees and moss, and you basically get to see outcrops by canoeing or having a motorboat. So that's why you'll see a lot of the outcrops are wet, because they're literally at the lakeshore. Here's some, I put Woman Lake together. They are separated by several hundred kilometers, but as we've recently showed, they have the same age within error. And we consider them part of the same platform. And here you can see some lovely microbialites from the Woman Lake package. Why is all this important? Why am I showing Archean carbonate packages like Steep Rock Lake and Red Lake and Woman Lake? Well, because of the importance of carbonate platforms for Earth's carbon cycle. Here you have a picture of the Bahamas taken from space. And the Bahamas is 7 kilometers of pure CaCO3. And there's something like 50,000 times more CO2 trapped in that 7 kilometer thick carbonate package than there is in our entire atmosphere today. So this represents this is the major long-term sink for carbon at Earth's surface today. So understanding how the Earth finally figured out how to trap carbon into carbonate platforms and eventually let them be subducted is really important. Here's a kind of a global view of the carbon cycle, what we call the long-term carbon cycle. This is the carbon cycle considered on million-year timescales, where ultimately carbon is degassed from the mantle and is then converted from atmospheric CO2 back into bicarbonate via continental weathering of silicates and carbonates. This excess bicarbonate, it's in excess of what would normally just dissolve from the atmosphere. There's obviously an equilibrium between CO2 gas and the water, but what's added by weathering is in excess, and it is ultimately transformed into sediments, whether it be CaCO3, so carbonate minerals, or organic matter, and eventually subducted. And this completes Earth's carbon cycle. And on million-year timescales, what comes out of volcanoes goes back into subduction. And the Earth has been maintaining this balance for billions of years. And thankfully so, because what happens if you don't have a balanced carbon cycle? You become Venus. Venus is the result of 4.5 billion years of one-way mantle degassing without any way to take CO2 back into the mantle. And so that's one of the motivations of looking at these carbonate platforms, and it kind of what makes them a biosignature. They are biological deposits. All of those things that I showed you, the 400 meters of Steep Rock Lake carbonate, the 250 meters at Red Lake, it's microbialitic all the way through. Here you can see the thicknesses of carbonate occurrences on the early Earth before 2.5 billion years ago. Here's Campbell Rand Malmani. Here's Steep Rock Lake. Here's Woman Lake, and here's Red Lake. So we really are looking at Earth's carbonate factory ramping up with time. Why, you might say, why, Stefan, aren't there carbonates on the early Earth? Well, the same reason that by increasing atmospheric CO2 today, we're making it harder for corals and shellfish to live. It's harder to make their skeletons as we increase CO2 and we acidify the oceans. Well, try cranking up the CO2 100, 1,000, or 10,000 times like we believe it was on the early Earth. It becomes very difficult to form a carbonate. And these are still questions that are at the limit of our knowledge. We still know very little about how all this stuff happened on Earth. And so I would consider that global carbonate production is a biosignature, personally. Okay, So, moving on, we got to get through our top 10 to the Chobeni carbonate in the Nsuze group. It is missing from that graph I showed earlier, and I'm going to have to add it manually. But here, at 296 billion years ago in South Africa, you have about an 80-meter thick stromatolitic carbonate. It's not all stromatolitic. It's actually mixed siliciclastic carbonate, a lot of carbonate sand as well. So you don't have 80 meters of stromatolites. But when you do have stromatolites, they are incredibly gorgeous. These are some of the most, they're heavily silicified, and you can really see the individual layers of the ancient mats poking out as the carbonate weathers in and the silica resists weathering and sticks out. And they're really, really gorgeous. Here's another photo from the field. Here we are on the outcrop. We're all just so happy. We're taking photos of each other next to the outcrop. And this is me in front of it, and I regret I could not find a photo without me in it. But here what you see are these linked columns rising up on this side and giant domes on this side of me. And I have to find a photo where I'm not sitting there smiling my face off because I'm so excited to find this outcrop. Okay. This here at 2.96 billion years old, we're very close to the iron formations where I showed you that molybdenum isotope evidence. And further work on these carbonates of the same age as those iron formations have shown some remarkable trends in iron and sulfur stable isotopes that are consistent with oxygen production in shallow water environments. Basically, what you can see is that iron isotopes are going lighter and lighter as sulfur isotopes go lighter and lighter. And this is best interpreted, most straightforwardly interpreted as iron being depleted out of the water column by oxidation, while the sulfate reservoir gets more and more important. So we're looking at, and that's why the fractionations are getting larger and larger in sulfur, and the iron isotope compositions are getting more and more extreme. It's because we're titrating out the iron and growing the sulfate pool. So that's how this data is interpreted at present. It indicates both iron reduction and sulfate reduction in these settings as well. Okay, moving on, number 5, microbial mats of the Moody's group. So here we're gonna shift gears a little bit. We're now in the Barberton Greenstone Belt. We're gonna pass a little bit of time. So we're here in South Africa. There's the Barberton Greenstone Belt. We have 3 groups. The youngest, the Moody's group. Then we have the middle-aged brother or sister, the fig tree, and then we have the older Onverwacht. And you can see the Moody's group outcrops here in kind of yellow. Here's a stratigraphic column, and what you're looking at here is Earth's oldest preserved emerged coastline. In fact, so this whole sequence is about 4.5 kilometers thick, and it starts at the bottom with alluvial, possibly fluvial deposits. This is Earth's oldest kind of emerged land mass and maybe river. In any case, alluvial fan. And we see kind of a finding upward system, but there's a lot of diversity here, and this is a really complex system that's been so interesting that we actually got funded recently. Christoph Heubeck, a professor in Germany and a friend to many of us, he led an ICTP drilling project, and we procured something like 7 drill holes, 3.2 kilometers worth of drilling. It took 18 months drilling day and night with 2 drill rigs for $2 million US. And the drill course just arrived in Europe about a year and a half ago. So we're all working hard on that. I hope that maybe next year I can show you something exciting from these drill course. Anyway, why are we going to the Moody's group? Not just because it's the first beach, it's the first emerged coastline. It's where we find the first evidence of anything in contact with the atmosphere. And what you have here are mud cracks in Moody's sandstones. So this is the first time that we have evidence that something on Earth actually dried up and was out of the water. And so that's a quite remarkable sample. And so the Moody's has a lot of things to show us. It also has these what we call microbially induced sedimentary structures, what are interpreted as tufted microbial mats. These are interpreted as compressed microbial mats living on the beach, much as you might see green algae coating sand in certain places on the beach today. In fact, Martin Homan, who did his PhD with Christoph Heubeck and then came and did a postdoc with myself, he spent most of his PhD mapping these things out, and he can trace out these microbial mat party zones in the Moody's group across 15 kilometers here. strike, which is quite remarkable. These were really large, happy, thriving microbial communities. And he wrote a really nice paper comparing what you see in these 3.22 billion-year-old rocks with modern microbial mats. And here you can see what he calls tufts and gas domes. So in modern microbial mats, oxygen production will sometimes lift the mat up and make little TP structures and gas domes. Well, with tufts on the top of filaments kind of poking out, and you see remarkably similar things in the 3.2 billion-year-old Moody's group. And then finally, in 2000, when he came and did a postdoc with me in Brest, we did some carbon and nitrogen stable isotope analyses of both marine microbial mats and microbial mats that Martin found draping conglomerates in the alluvial fluvial plain, which represents probably the oldest emerged biosphere that we know of. So the oldest rocks that we have cleared that were out of water seem to have microbial mats living on them already. Okay, and they show contrast in their stable carbon and nitrogen isotope compositions that are also indicating different nitrogen sources. We chalked up a potential, we implied a potential lightning nitrate source coming off the continents, and also different carbon acquisition and cycling strategies. These were probably complex communities. We're not talking about one microorganism. We're talking about how the community itself does as a whole, almost certainly. Okay, moving forward, number 4, to the Buckreef Chert. So now we're still in the Barberton Greenstone Belt. We're moving into the oldest Ampferwag group, and we're going into the, and we're looking in the Kronberg Formation, around 3.42 billion-year-old sediments. We have these lovely banded black and white cherts with these kind of crinkly layering of organic carbon that really looks like microbial mats as well. Just a little bit less flagrant and spectacular than you saw in the Moody's group. Now what's kind of interesting is Kieran Hickman Lewis, who is at the Natural History Museum in London and is now a professor in London, he used this, and he used these outcrops to test Mars on-surface sample and sample return strategies. So what they actually did is that they simulated the analyses that we might expect to be able to do on Mars using Raman spectroscopy and X-ray fluorescence mapping using Earth analogs. And this is probably the best analog. Someone asked the question, could you take your lab tools to the outcrop? Well, this represents one of the most recent attempts to kind of intercalibrate what an instrument you could put on a rover against ancient life traces on Earth. And it's kind of interesting. Here you kind of see this is the kind of data from what most people consider a this is a very ancient, highly probable evidence of life on Earth 3.42 billion years ago, and this is the kind of data that we might expect to get, from a rover. I don't know if you see life in there. The positive thing is what you can see is the Raman is detecting organic carbon very clearly, so that's nice. But the X-ray fluorescence, using elemental relationships in sediments to identify life is still, shaky grounds. So, but anyway, people are trying it. For the person who had a question earlier in the school. All right, we're getting up to the top 3. Getting to the Panorama Formation, and I've lumped the Dresser and the Strelley Pool Cherts together. And so we're in the Pilbara Craton, Western Australia. The Strelley Pool Chert is 3.43 billion years old, and the Dresser Formation is 3.48 billion years old. There are a couple hundred meters separated from each other in the sequence, so you can see one and then kind of go see the other. This is a landmark paper by Abigail Allwood, published in Nature in 2006, describing a stromatolite reef based on observations of stromatolites in the Strelley Pool Chert at 243. And they are just spectacular. You see a whole diversity of structures. Here are photographs and here are drawings in the paper that describe all the different morphologies that are seen in the Strelley Pool Chert. I also got a chance to go there as a student, so here I am. I often have a selfie smiling my face off before selfies were cool, when I was a PhD student more than 10 years ago, 15 years ago. So those stromatolites are just spectacular, and really nobody on Earth, I believe, would say anymore that there's any doubt about their biogenicity. Getting to the Dresser, 3.48, it's a little bit it was a little bit shakier. They're highly weathered. There's not a lot of stromatolitic horizons. But then in 2019, new drill cores were obtained, short drill cores through the Dresser Formation to look for stromatolites. And here are some of the images of what they found in these highly fresh samples, taken from deep in the subsurface. And here the stromatolites are pyritized, which is quite remarkable. And so it also testifies to how they escape surface oxidation. Not to say that this pyrite is necessarily primary. Could this be a secondary sulfidation, billion years after deposition? Sure. And these are some questions that we still have to address. Really, someone should date the sulfide phases in these things with rhenium osmium. That's what we want to do next. Anyway. So here's another picture of some of these stromatolitic, these pyritized stromatolites from the Dresser. This is a pretty recent paper from last year where there's kind of a model shown. There's kind of two occurrences of stromatolites that occur there. You've got stromatolites that grow up into kind of sand. And they're interpreted as being in this kind of subtidal calm pools. And then there's these small stromatolites growing up into kind of barite. And this is interpreted as being a more hydrothermally influenced environment where hydrothermal fluids are kicking barium out that's mixing with the trace sulfate that's maybe being delivered atmospherically to make this kind of briny, salty version where the stromatolites grow into barites. All right, number 2, graphite in the Isua supercrustal belt. Okay, so this we're going to get into some pretty controversial stuff. We're leaving 3.5 billion years old behind us, and we're going older. And these things are necessarily controversial. And I'm not going to tell you that any of the things you see here is life or not. So don't ask me. No, I'm just joking. You can ask me. We're jumping over to Greenland, the Isua supercrustal belt. Here is the locality of Isua. Relative to Greenland. These are images from a nice review by Nutman and Friend in 2009 that presents new maps for the Isua supercrustal belt. Here you can see rare earth element spectra for banded iron formations, which you can see pictured here from the Isua supercrustal belt, that show clear seawater signatures. I won't go into a lot of detail, but you have positive lanthanum anomalies, positive yttrium-holmium ratios, heavy rare earth element enrichment compared to light, and strong europium anomalies characteristic of hydrothermally influenced Archean seawater. All the signatures of seawater are there, except it's missing the oxidative signal. There's no cerium oxidation, and we have this whopping hydrothermal influence that we don't see today. Otherwise, it resembles modern seawater, which is quite remarkable for 3.8 billion-year-old rocks. There's been an important debate about traces of life in these sediments that's spanning back over 20 years. In 1996, Stephen Moises and co-authors published a paper in Nature of evidence for life on Earth before 3.8 billion years ago. And what is it based on? Here, this is based on the carbon isotope composition of small graphite inclusions in these sediments. Okay, and so here you can see the carbon isotope composition of, say, Pilbara sediments, like we just looked at, where people don't have much doubt that this is biogenic in origin. And then we have Isua and also Aquilia Island, which is an island off of Greenland of similar age, but more dubious sedimentary origin. And I won't even go into that debate. But anyway, what you can see here is carbon isotope compositions consistent with classic Rubisco fixation of carbon. Isotopically light, minus 20, minus 30. As we get lighter, this is more chemotrophic or maybe methanotrophic as you get down here. In any case, this is consistent with life, but there's something you have to keep in mind, is that it's not the only way to make these light carbon isotope enrichments isn't life. We have something called the Fischer-Tropsch process, which is synthesis of organic matter abiotically. And fractionations of this magnitude or greater have been observed experimentally in Fischer-Tropsch synthesis of organic matter abiotically. So this is consistent with life, possibly, but does it absolutely require it? No, not necessarily. Okay, and now we talked about graphite and stromatolites. This is there was a recent. This is all relatively recent, in the last 10 years. Dueling Nature papers. Okay, one showing these sedimentary structures in newly discovered carbonates The Isua outcrops are at the edge of a glacier that's sadly receding, and new outcrop is exposed every year. And what was exposed recently were carbonate rocks at Isua, which were previously generally unknown, at least carbonate rocks that seem to be sedimentary. Nutman and colleagues observed these structures, and they called them putative stromatolites, and maybe we have photosynthesis at 3.7 billion years ago. Then you get to, there was a short, this was kind of a reactionary force. Very quickly, people from the U.S. organized helicopters and got out there as soon as possible and took new samples. Very American, swooped in on big helicopters with drills and everything. But they did some really great work. And what they saw was, in fact, these structures don't always point up. Uh-oh, that one's pointing down. Is this really a stromatolite? They should really only point in one direction. Furthermore, if you look, they notice that these features, these kind of domical and pointy features, are only observed on, if you look at a rock that's cut on two faces that are orthogonal faces, you only see the structures on one side and not the other, which they interpret as this is the extensional direction and this is the compressional direction, making these structures secondary. Now, I gotta say, we've been analyzing these carbonates as well in my lab, and they do look genuinely marine for 3.8. So that's quite exciting on its own. Whether they contain fossil stromatolites or not, well, the debate's still raging on. Okay, getting to number 1, filamentous microstructures in the 3.8 billion year old Nuvvuagittuq greenstone belt. So now we're here back in Canada. We're at the northern tip of Hudson's Bay here, and out here you have something called the Nuvvuagittuq greenstone belt. And it's between 3.8 and 4.3 billion years old. The problem is the multiple chronometers people have thrown at these rocks don't agree. Uranium lead on zircons, which is really the gold standard, very reliable, indicates 3.8 billion years old. Classic samarium neodymium dating also indicates 3.8 billion years old. However, isotopic anomalies in rare isotopes of neodymium indicate 4.3. So anyway, that's just so you're aware. There's a debate on the age of these rocks, but no one would say that they're younger than 3.8 billion years old. The sedimentary protoliths are clear. They contain abundant biff and jasper, and these are clearly marine sediments. There's no question about that. And they host some remarkable filamentous structures. On the left, you see these are from the Nuvvuagittuq greenstone belt, 3.8 billion years old. And here you can see it's labeled Loken because it's from the Loken ophiolite. So this is a piece of this is much younger crust that has been exposed, where there are also jaspers, where we see very similar carbonaceous filamentous structures. And the real kicker from this Dodd paper in Nature is this image here, at least for me. These are hematite encrusted tubes consistent with bacterial filamentous origin, poking up in pure chert, highly resistant mineral. This all looks pretty clean. If you're going to say that this isn't life, you have to say this is some kind of biomorph, some structure that just happens to resemble a bacterial cell, or you have to say that it's secondary, and some bacteria at some point in the history of this rock climbed up in there and munched its way in, which has been known to happen as well. But in Canada, these rocks are really fresh. Like I said, they've been recently deglaciated. They haven't been rotting or weathering profoundly at the surface for 40 million years, like in South Africa or Australia. Okay, so that's my top 10. I've got a couple of honorable mentions. There is a tantalizing chance that we can go even further with the sedimentary record. There's in something called the Saglic block up here between, this is Greenland, Isua's up here, and there is the Saglic block. And here, quite exciting, it's mostly been a Japanese team mapping out there and doing some analyses, and they found a whole diversity of sediments, including carbonates, iron formations, and peelites, which are basically metamorphosed mudstones and shales, abundant outcrops up there, and they've been cross-cut by veins convincingly dated to 3.95 billion years old. And the metamorphic grade appears to be upper green schist, lower amphibolite facies, a little bit better than Isua. So I forgot to show you a piece of Isua that I have here, where you can see this is banded iron formation from Isua. I brought a magnet here, so you can after the talk, feel free to kind of scrape the magnet along the layers. It's you can really see the banded iron aspect of it. But if you can see this rock, you see how shiny it is. The magnetite has been highly recrystallized into this really brilliant shiny magnetite. This rock has seen 800 degrees Celsius probably, whereas at Nuliak metamorphic temperatures and pressures seem to have been lower. So I know where I'm trying to go next for my next big project. So there's rare earth element data showing that these are marine sediments. There are organic carbon data that's also isotopically light. This is all very promising for a new site that might take us further than the heavily metamorphosed Nuvuwakatuk and Isua sites. Moving forward, and there's one last honorable mention, and this ties in nicely with what Nadia presented, is that going back even further, there is the study by Bell et al. They looked at 10,000 zircons. They found one with a graphite inclusion, with a carbon isotope composition consistent with a biological source. That deserves an honorable mention. It's quite a rare object. All right, so to conclude, Earth has a rich fossil record and biosignature record spanning 3.8 to 2.6 billion years old. And I showed you some of the highlights of those localities and what we actually see in the field and what we take into the lab and analyze. We've barely scratched the surface of this record. Each of these sites only has maybe a couple or a handful of studies published on them. It's really, the field's wide open for people to go and do more work like this. I'm surprised people aren't crawling all over these outcrops, considering how important I consider them for understanding Earth history. I consider these as important as moon rocks, to put in perspective. And then understanding, I'd just like to finish on an astrobiological point, is that in understanding how early life on Earth is preserved in sediments and how it began taking hold of Earth's biogeochemical cycles, I think is pretty obviously important for astrobiology, whether we're searching on Mars or exoplanets. So with that, I'd like to thank you for your attention. Thank you very much.